Welcome to the introductory video for the Touch and Mid-Air Framework Visualizer. My name is Richard Lopez and I am the developer and Scrum Master for the version 1.0 of the TAM Visualizer. The problem at hand. The problem at hand, it is an explosion of many input devices such as mid-air, full body tracking, multi-touch, motion sensors, gamepads, combining touch and styluses, movement tracking, 3D mouses, and inputs with feedback. It is too cumbersome for developers to code for more than one device at a time. They have to go through the API of the devices and search for the functions that they want to use. This creates a time-consuming task. There is no library at the moment to code for any of these input devices. There is no tool that unifies more than one input device. We want to provide a modern code base so you can have a system that contains the information for all these input devices so that you can use them as you want. We want to provide a tool for researchers and users to allow for a more simplistic approach to connecting more than one device, or to use one device without the need to go into the deep code of that device. We also would like to promote diversity via human-computer interfaces so that a new generation of developers can code for a new generation of games and applications. There's one existing system at the moment called the Virtual Reality Peripheral Network. This system connects virtual reality devices via a remotely hosted server that contains all of the definitions for these devices. The problem with this is that it's a server, therefore there's a time delay that will affect the performance of those devices. There might be interruptions whenever the server goes down, and it is still not general enough for non-virtual reality peripheral. It is important for virtual devices to have an immediate feedback because of the amount of information encoded into every single command. This is the project schedule for version 1.0 of the visualizer. We are using an agile approach to the development of this software. In this approach, we are splitting up the work into different sprints, 5 to be exact. During each sprint, which is a length of 2 weeks, we have scrums, which is basically the work that needs to be done during that sprint. At the end of each sprint, there is a meeting with the product owner to validate that the work is the one that the product owner asked for, and also to include any other feedback that the product owner desires to include into the next sprint. The implemented user stories for the TAM visualizer are as follows. Visualization. The idea behind these user stories is to allow for the user to draw on the screen and be able to obtain a visual representation of that drawing. Input domain. This user story is about the input when a touch event happens, so that the system utilizes the information from that touch event. Manipulation. This user story maps the input via a mapping function into a different output domain. This pertains to the output displayed to the user. The state user story keeps track of the state of the touch event. This can be touching, moving, or not touching. The events user story pertains to whenever a touch event happens on the screen. The user interface is a GUI designed for the user to be able to select multiple options, such as change the size of the brush, clear the screen, save the data, open previously saved data, selecting a mapping function, and any other function that needs to be implemented in the future. The save data user story gives the ability for the user to be able to save all the touch events that have happened. The playback user story plays back all of the touch points that were previously saved by the user. The complete visualizer user story basically encompasses all the other user stories so that a complete visualizer can be used. The use cases. The use cases implemented are as follows. The system shall subscribe to a Windows service to receive touch events. The system shall allow a user to touch the screen with one or more fingers. The system shall define the states of a touch event. The system shall use the X and Y coordinates and map them to a function. The system shall record input. The system shall replay the touch action in the order the order the action happened. The system shall allow for input to be saved to a file. The system shall read recorded input files and replay them. The system shall allow various sizes of touch visualization. The system shall allow the user to clear the screen and replay data at will. The system shall display all the information from the program to a debug monitor. This is the use case diagram for the Touch and Air Motion Framework. In this use case diagram, we can see that there's two actors, an application developer, which is the main actor, and a system, which is a secondary actor. The system is only used as a message interface between the input device and our application. Therefore, you can see that with the system there's a connection, a subscription, an interpretation, and the states of the touch events registered by the input device. The application developer deals directly with the mapping function, the clear screen, drawing, manipulating that drawing, the playback, and recording input. Here we see the sequence diagram for the subscription use case. The draw sequence diagram. Here we see the state sequence diagram. Here we see the mapping sequence diagram. Here we see the input recording sequence diagram. Here we see the replay sequence diagram. Here we see the playback sequence diagram. Here we see the save to file sequence diagram. Here we see the playback file sequence diagram. Here we see the resize sequence diagram. Here we see the clear screen sequence diagram. The system decomposition was created using two different architectures. The service-oriented architecture, which is basically a message passing architecture. This is seen in the connection subsystem, which is subscribed to a Windows event. The second architecture uses the model view controller. In here, the visualization is the view, the device is the controller, and the connection is the model. Any changes in the connection will alert the device or the visualization. The system deployment. The hardware necessary to run the TAM visualizer at the moment is a touchscreen capable computer, a multi-touch screen capable computer, a 1 GB of RAM, and 512 MB of a video card. The software necessary is a Windows operating system 8.1 or greater with the ability of multi-touch, Visual Studio 2013 or greater. This is because it includes C++11, which is the language used for this, and the Qt plugin for Visual Studio 5.4 or greater. In the right, we can see the deployment diagram for the TAM visualizer. The device, in this case a touchscreen, communicates to the rest of the system via bus. The rest of the system is running on a Windows operating system. We have three different classes: the main window, the draw area, and the debug. And then we have an input file. The only persistent data in this system is whenever a user wants to save a file of all the touch points. The file is saved as a list of touch points in chronological order. A touch point object consists of an X coordinate, a Y coordinate, an ID, and a timestamp. In the image to the right, we can see that the file is saved as a comma-separated value file. Security and privacy. The TAM visualizer and the TAM framework do not utilize any form of registered user. There is no private data kept, and the framework is aimed towards developers as well as the open source community. Therefore, there is no privacy or security implementation. The detailed design. Here is the static view for the TAM visualizer. As we can see, the TAM visualizer consists of three different classes: the draw area, the main window, and the debug. Here we can see some of the functions and attributes of each class. The dynamic view for the main function in the TAM visualizer is the touch. This state machine goes through all the different states in which a touch event can happen, being a default state or not touching state, to a touching state or going back to a default state, going from a touching to a moving state, going from a moving state to a non-moving, which can either be a touching state or a default not touching state. Once all the inputs are done and the system is closed, it goes from the default state to a quit state. For every use case in the TAM visualizer, we have a test case. Two test cases for the touch use case can be seen here. The first one is a sunny day test case in which everything happens in accordance to the use case. The second one is a rainy day test case. In here, events happen different than in the perfect use case. In the sunny day use case, we can see that the visualizer is started, an input at coordinates 50, 50 is created, the touch event is sent, and a red circle is drawn at the screen at the coordinates 50, 50. In the rainy day test case, we can see that the visualizer is started, the input is given as 50 and -50, and the event is passed. Since the Y coordinate is a negative number and the screen goes from 0 to maximum number of pixels allowed in the screen, no red circle is drawn. Here we have test cases for the save use case. Here we have test cases for the replay use case. Here we have test cases for the save to file use case. Here we have test cases for the open file use case. Here we have test cases resize brush use case. Here we have test cases for the map use case. Here we have test cases for the clear screen use case. Now it's time for a demo. In this demo, we will be using from 1 to 10 fingers. All the fingers will be color coded. Here we go. We can see that as we move our fingers through the screen, lines get created with the color coded fingers. We can choose to immediately replay whatever we just did. We can see an exact replay of all the events that I painted. We can now choose to clear the screen. I will now use one finger to write on the screen. We're going to play back the event. Now choose a map that will make the output 2 times that of the input. So if I start in the top left corner of the screen and I start drawing and I move in a diagonal, you can see that the 2D representation is ahead of my finger by twice the amount of pixels that the coordinates. When the 2D representation ends in the bottom right corner, my fingers has only reached the middle of the screen, as we expect. We can now choose a map of 3, which is 1/2 the output to the input. So if I start at the bottom right of the screen, the 2D representation starts in the middle of the screen due to the half mapping. As I move to the left part of the screen, I get closer and closer to the actual 2D representation until it is 1:1. Now I choose to use the mapping for 1. I clear the screen. I can now move my fingers throughout the screen once again. And they are mapped 1:1, meaning wherever I touch on the screen, in that immediate place, in that exact coordinate, the drawing will appear. Let's now open a file that I have previously created called test. We double click, and a replay is happening immediately of the touch points in that file. We clear the screen. Let's now create our own file. We can save that file, choose a name for it, test2, press enter, and the file has been saved. We can clear the screen, play back that file, we can open the file that we previously opened, test1. We can clear the screen and open the file that we just saved, test2, and we can see that the replay is that of the file that we created second. This is it for the demo for the TAM visualizer. This is the end of the TAM visualizer video. Thank you very much for your attention.